The asteroid's first day was only the beginning. The extinction accelerated when sunlight itself began disappearing from Earth. Rock dust, soot, and sulfur aerosols entered the atmosphere together, but each would block sunlight in a different way. Fine dust scattered light, soot absorbed it, and aerosols reflected it. Different particles.
High-altitude winds spread the impact cloud across hemispheres, turning one crater into a planetary atmospheric event.
For many survivors, the next sunrise arrived weak, red, and unfamiliar. Daylight no longer behaved like daylight. Surface light fell sharply. Even places untouched by blast, fire, or tsunami began receiving less usable energy. Photosynthesis did not stop everywhere at once, but the energy entering ecosystems had already begun to fall. The crisis began at the bottom. When primary producers weakened, every consumer above them inherited the loss. Normal night still crossed the planet. Behind it came a darkness that did not end when morning returned. Impact winter was not a single dark afternoon. Its duration depended on how long dust, soot, and aerosols remained. Sulfur gases formed reflective aerosols that reduced solar heating, although the total sulfur released remains scientifically debated. States silicate dust, as meaning that the tillis meating tubit, low-range dust, low sunlight.
Soot absorbed light instead of reflecting it, potentially adding another layer of darkness to the developing winter.
Three mechanisms, scattering, absorption, and reflection, work together to cut the energy reaching Earth's surface. Scientists agree the impact caused severe dimming. The exact balance of dust, soot, and sulfur remains an active research. From orbit, Earth still received sunlight. The problem was how little of that light could penetrate to the living surface. Darkness was global, but not perfectly uniform. Latitude, clouds, and particle density shaped how much light survived. Light disappeared faster than heat. The sky darkened within hours, while the full cooling unfolded more slowly. Once incoming energy collapsed, global temperatures began falling. Land cooled rapidly, the oceans responded more slowly. This was impact winter. Darkness above, cooling below, and a shrinking energy supply connecting every ecosystem. Even the tropics lost warmth. Ecosystems adapted to stable heat, suddenly faced cold, dark. Seasonal rhythms were disrupted. Growth, migration, and reproduction no longer matched the conditions organisms had evolved to expect. In some regions, freezing conditions may have reached ecosystems with little protection from sudden cold. Climate models produce different numbers, but they consistently point toward abrupt, biologically dangerous cooling. Oceans stored heat longer than land, delaying the cold, but not shielding marine food webs from darkness.
Land and ocean cooled at different speeds, but both suffered from the same collapse in solar energy.
Cooling and dimming disrupted the water cycle, changing rainfall patterns already destabilized by impact debris and atmospheric chemistry. The atmosphere did not simply become colder, its circulation changed, redistributing clouds, wind, and precipitation. How long the darkest phase lasted remains uncertain, because different particles settled, reacted, and circulated at different rates. Darkness reduced food production. Cold increased biological stress. Together, they made recovery far more difficult. Plants survived the blast in many places, but surviving was different from growing under a darkened sky.
With less light, leaves produced less energy. Entire plants began running on stored reserves instead of new growth.
Roots, seeds, and underground tissues offered temporary protection, allowing some plant lineages to wait for better conditions. Forest decline removed more than leaves. It dismantled shade, nesting sites, moisture, and protection from predators. Burned landscapes faced a second crisis. Darkness and cold prevented rapid regrowth after the flames had passed. Ash and dust could reduce the little light that remained, adding physical damage to atmospheric darkness. Dead vegetation briefly fed decomposers, but recycled material could not replace a functioning photosynthetic system. Even where vegetation remained, it could be sparse, damaged, or nutritionally poor for large herbivores.
Extinction pressure grew because plants could not recover quickly enough to support the animals depending on them.
On land, the collapse moved upward. First plants, then herbivores, then the predators that depended on them. The ocean's most productive layer depended on sunlight. As that layer dimmed, the marine crisis began at microscopic. Plankton could survive brief darkness, but prolonged low light reduced growth and reproduction across enormous ocean areas. Marine productivity fell unevenly, but the global direction was clear. Less light meant less new biological energy. Some plankton faced a double burden: low light above and disrupted seawater chemistry around them. Dead plankton created a temporary food pulse below, but the deep ocean eventually received less fresh material from the surface. Ammonites survived earlier crises, but this collapse removed the productive marine system supporting their entire life cycle. Top marine predators were buffered from the impact only briefly. Their survival still depended on prey below them. The deep ocean avoided the worst surface heat and fire, but not the slow loss of food produced above. Coastal ecosystems faced both physical destruction and the global decline in sunlight-driven productivity. The marine extinction was also bottom-up. Microscopic producers failed first, then larger animals followed. Many non-avian dinosaurs probably survived the first day. The longer crisis was finding enough energy to remain alive. Large bodies required large, reliable food supplies. Impact winter made that ecological requirement increasingly impossible. Migration could escape a local fire or drought. It could not easily escape a planet-wide collapse in productivity. Water remained available in many places, but ash, sediment, and habitat damage made dependable resources harder to find. Extinction is not only about adults dying. It can begin when populations stop replacing themselves. Young animals face the same darkness and cold, with smaller reserves and complete dependence on damaged ecosystems. Body size shaped risk. Large animals needed more energy. Small animals could survive on less and hide more effectively. For large dinosaurs, the problem was not one missed meal. It was sustained scarcity across weeks and months. Starvation propagated through the ecosystem, turning plant failure into animal decline and then predator collapse. Non-avian dinosaurs were not defeated by one weapon. They faced a system-wide failure they could not outlast. Predators experienced the crisis one step later, but prey loss ultimately reached them with equal force. Carrion created a short-lived resource pulse, but dead animals could not sustain predators indefinitely. In the Nentry demand and milsing donations and subsicitions to the Cotramitsa system. Syncopations, the same ecological logic operated at sea. Top predators could not survive after their prey base disappeared. Specialists were vulnerable when one essential resource vanished. Generalists could sometimes redirect their diets. Ecological redundancy mattered. A web with alternatives could bend where a narrow chain simply broke. Post-impact abundance could be deceptive. A burst of carrion was followed by a much longer period of scarcity. The longer darkness persisted, the more survival depended on reserves, low energy needs, and adaptable behavior. Small size did not guarantee survival, but it reduced several risks at once: food demand, exposure, and recovery time. Extinction was selective, not random. Biology, geography, and chance combined to decide which lineages crossed the boundary. Burrows reduced exposure to heat, cold, fire, and falling debris. 4 immediate and 1 small refuge. Freshwater systems offered shelter and stored organic matter, buffering some survivors from immediate food collapse. Water and sediment softened temperature extremes and protected organisms from some of the surface chaos. Detritus-based food webs could continue using dead organic matter after fresh plant growth collapsed. Fungi helped recycle dead material, supporting small food webs where living plants had become scarce. Seeds could wait. Dormancy allowed some plants to survive conditions that active growth could not tolerate. Insects linked seeds, fungi, and detritus to small survivors, keeping some food pathways active. Small mammals combined shelter, flexible diets, and modest energy needs, traits well suited to a damaged world. Some bird lineages may have benefited from small size and seed-based diets, although survival differed among groups. Low energy demands and aquatic refuges helped crocodilians and turtles survive conditions that eliminated many larger competitors.
Birds were dinosaurs too. The extinction erased non-avian branches, while a few avian lineages survived.
Ground-level feeding may have helped some birds after forests collapsed, but the evidence remains incomplete. Flight alone was not enough. A flying animal still needed food, shelter, and a functioning place to land. Dietary flexibility allowed some survivors to switch resources as familiar food chains disappeared. Smaller survivors could rebuild populations faster, but only if enough food and shelter remained. Mammals survived not because they were superior, but because many were small, flexible, and sheltered. Nocturnal habits may have made darkness less immediately disruptive for some mammals. Energy-saving states may have helped some small animals, although direct evidence for specific behaviors is limited. Freshwater refuges repeatedly appear among surviving groups, suggesting these systems buffered several forms of stress. No single trait guaranteed survival. Outcomes emerged from combinations of biology, geography, timing, and the extinction is preserved worldwide as a thin boundary separating the Cretaceous from the world that followed. Soot and impact dust in boundary sediments record the atmospheric material that spread around the planet. Iridium and impact glass identify the event's extraterrestrial source and its global reach. Climate proxies preserve abrupt environmental change, supporting a world that became darker, colder, and less productive. Fossils show abrupt biological turnover. Many dominant groups disappear, while a smaller set of survivors remains. The post-impact fern spike records pioneer plants colonizing landscapes where mature forests had vanished. Some records suggest increased fungal activity after the impact, but the pattern is not equally clear everywhere. Marine microfossils record a sharp crash in plankton diversity, and productivity at the boundary.
Plant fossils record severe ecological disruption, although the exact pattern varied from region to region.
Models explain mechanisms. Rocks test them. The strongest conclusions emerge where both lines of evidence agree. Weeks after impact, darkness and cold continued, while survivors depended on stored food, detritus, and protected habitat. The longer the veil persisted, the more temporary advantages became exhausted. Eventually, particles settled and reacted out of the atmosphere, allowing sunlight to begin returning. More sunlight did not instantly restore ecosystems. Food webs had already lost species, structure, and biological memory. Dust, soot, and aerosols did not disappear together. Their different lifetimes shaped the pace of recovery. Chemical disruption outlasted the darkest sky, continuing to stress soils, lakes, and oceans. Recovery began with opportunists, able to colonize damaged landscapes, not with the return of old forests. Ferns expanded quickly in many regions, marking recovery, while also revealing how completely forests' early recovery ecosystems were simpler, less diverse, and built around the survivors that remained. Survivors eventually expanded into emptied ecological roles, but rebuilding complex ecosystems took far longer than. When the sun returned, it illuminated a planet that was warmer and brighter, but biologically transformed. Sunlight returned, but non-avian dinosaurs did not. Their ecological world had already collapsed beyond recovery. Mass extinction created ecological vacancies, changing which lineages would shape the future. Mammals did not instantly dominate, but surviving lineages later diversified into opportunities created. Every living bird is evidence that one branch of the dinosaur family survived the winter. The asteroid did not finish the extinction in seconds. It triggered a chain of planetary failures. The decisive weapon was not the crater alone. It was the collapse of the systems connecting sunlight to life. Complex food webs can be powerful in stable worlds, and dangerously fragile when their energy source disappears. The year the sun disappeared did not erase all life. It decided which lives would inherit the planet. The asteroid opened the crisis. Impact winter finished the dinosaur world and made the modern one possible.